thank you for inviting me again to this talk. So today I will talk about combinatorial two-sided search. I think the name two-sided search is a little bit strange, but I will tell you what it means. So before I start, so the talk based on two papers somehow. So the first paper is with Harut, Ferdinando, and with Valotia. It's about a combinatorial model of two-sided search. You can find this paper. I think I also sent it to Jula. He can forward it to you if you are interested. And the second one is together with the son of Valotia. It's Alexei Lebedev. And somehow we found their additive version and of two-sided search. And then we look at faster objects. So we'll see what this means. Okay, so the talk I will start with introductions and the problem statement and for which work you can use this. And then you will see I will do search on parsers and cycles and also at trees. And then what does mean faster? So first the elements can move one step, and here you will see what it means that they can cast case steps. And at the end, I will also tell you what non-adaptive, what is possible for non-adaptive search. So first, search theory normally deals with a problem where if you have a searcher and a hidden object, and you want to find the element in minimum time. So and in the most early developments, it's assumed that an object to be searched is stationary and hidden according at the non-distribution, and it is not moving. So and this model is called one-sided search. You see here Alfred Renyi here. He of course have do research on this. So when you have an element and you want to search at it, and for some reasons, if you have no errors, then you can just do by the half strategy. You need a log of m if you have m elements questions, and then you can think about some errors perhaps which could appear, and also perhaps false answers. And of course, I add 100 because Alfred Renyi is also getting 100 years this year, and okay. So now we want to look at some case where the object can now be somehow active. So the object can move. So you have something like a line or like a circle, and now the object can move, so it can react. And this problem is called two-sided search. I don't know, really, it's not really a good name. I think two-sided search because it didn't search, it just tried to escape somehow. So this name comes from Bernard Koopman. So he did this during the Second World War. In principle, he wanted to find some submarine, and want to bomb it somehow. And in this case, of course, he can search for this submarine and can bomb it. And of course, the submarine tried to avoid this by moving. And his research was published then after the Second World War. So it was also theoretical, and there exists a book of him, and he gives the name two-sided search. So, and then we have a nice workshop. I think Jula was also there in 2010, and we talked about a lot of problems, and then we have a problem session, and then Rudolf Alswede, he asked the question, what can be done if we model this in a combinatorial way? Because Koopman did model it in a probabilistic way. So he modeled it in such a way that with some probability the element will be moved. And so he asked the question, what happened if we do it in probabilistic way? By the way, some of you know Rudolf still. They were guests when he was in Bielefeld. So, and this is a picture which was taken, I think, in 2002 or 2003, when he started to celebrating new PhDs in his garden. So it's taken in his garden. So I think starting around 2000, he offers always his garden to celebrate if some of his students got the PhD. And he also we drink a lot, and he also likes to make some fun with his parties. And you see him with the hat of, I think it was the celebration for Goa when she got her PhD. So what is the problem? So the problem is we must somehow define some object where the searched element can move. And we define an undirected graph. So we have n vertices, and E denotes the edges. And this is our search space. We have positions from 1 to n. And these are the vertices of the graph. And we know that the object can be found at some vertices at the graph. And this vertex is, of course, unknown to the searcher. And now the special thing now is that the object can move. So again, we can move we assume the simplest case. We can ask for every subset of this n here. And then we get an answer. The object is there and the object is not there. But after this answer, the target could be moved. And it could be moved along one edge. So it can be escaped somehow. So here it's written after each test, the target can move to any vertex adjacent to its current location and stay at the same place. Or it can also stay at the same place. Or it can move or it can stay. So you don't know what the object is doing. And the search is finished when the searcher is able to locate the object with some predefined occurrence S. So you can imagine it's not possible to say the object is at this vertex because it can move. So what we what is our goal? Our goal is please give S vertices and say the object is here, and after the movement, the object is still in one of these S vertices. So for example, if we say S is equal 5, then at the end of our procedure, we give 5 vertices, and even if the object moves by 1 after the final question, you can find it in one of these S vertices. So, and now, yes, the problem is now find the location of the target with this certain occurrence, and of course we want to do it in minimum time. So we denote now with small dj the location of the target at time j. So that's so you get such a vector, and this is a vector of vertices, and this defines somehow a walk in the graph. And of course, we have the test set. We denote by this t. We denote the test sets, and our function ft of d always gives a 0 if the object is not in the set, and it gives the 1 if it's in the set. Gives the yes. So, and tg is a test performed at time j. So we have a sequence of tests t1, t2, and we assume that our strategy have length n, and we call it sequential or adaptive strategy. That means after each question or each test, we get an answer, and depending on this answer, we ask the next test, and so on. And di is the set of possible positions of the target after the ice test. Because of the answer t1, we can reduce the number of possible positions, perhaps. For example, if we have the idea, we ask for half of the positions, and we know that the element moves by one edge with everything, then of course we can reduce the number of possible positions, and we denote them by di. Of course, in the beginning, all vertices are possible, and let us assume we ask the i's number, so the di is equal to the neighborhood. This gamma denotes the neighborhood of the i's test and the possible positions before. So di minus 1 is in possible positions after step I minus 1. And then we ask, of course, the next, or we did the next test. And then we join this. And then we have to look at the neighborhood because the element can move by 1. So if the answer is 1, if our test was successful, and it says the element is in this test region, then of course we can cut the test region with the number of possible positions before. But because the element can move by 1, we have to look at the neighborhood of this vertices. And of course, the other way around, if the test is negative, then we have to look at the complement sum. I don't know, is it clear or already some questions? So if you have some questions, please ask in between. Okay, it seemed to be clear. So now we have given a graph where with n and e, and a sequential or additive strategy of length n with a test t1 to tn. And now we call it GS successful for any possible sequence of target movements from d1 to dn if we have that the i's set of possible positions of the target is smaller or equal than s. That's exactly this precision I talked before. That's exactly the s here for some I smaller or equal n. That means because we are in an adaptive strategy, it will be different later in a non-adaptive strategy. As soon when we reach our goal, we just stop, because perhaps we stop even earlier. So you will see in the worst case, we stop at after n questions, but perhaps we can also stop earlier. And if we reach our goal earlier, then we say, okay, we can finish our search now. I can give this di as an answer. By S star of G, I denote the minimum number of S star such that there exists a G S star successful. As you saw before, it's never possible that S is equal 1, for example, because the element is always moving by 1, and we always assume that our graph is connected. So G1 is, for example, not possible. Then you have to think what is the smallest number, what is possible, and this we denote by S star. Furthermore, by small n of GS, we denote the minimum number, number of tests, such that we have a GS successful strategy of length n. So that means that ng of G and S denotes the minimal number of questions or tests we have. And such a strategy we call then GS, optimal GS strategy. So where can we use this model? So in principle, we first worked on it because of the question of Alswede. And later, when we want to publish it, the reviewers say, oh, okay, we can use this thing. And in principle, we have to thank the reviewers that we get this applications here. So one of the applications the reviewers told us is in the area of node selection for target tracking in tensor network. So when the task of the network is the tracking of object. So a major initial task is to determine an area where the object to be tracked is surely initially allocated, and from which the actual tracking procedure can start. And this location, together with the minimum of the area of localization, is one of the most critical and expensive part of the tracking procedure, as it is typically done by an exhaustive search. For the sake of reducing the bandwidth consumption, sensor networks are also hierarchically organized in graphs, and more specifically tree structures. Later, I will show you that we especially look at trees and try to solve the problem and have also some solutions. So that means our result can be used to support the localization phase by trying to reduce the area of localizations and reducing the number of activations of sensors. That's one application. Of course, it's also related somehow to group testing in graphs. So you can think about also to do group testing with moving elements. I think at the moment it's only considered with fixed elements. So it's here, however, in all these works, basic assumption is that the target is still, which makes problems significantly different. So another research related to this problem is of course graph searching. So, and models of search to our peers here, it's a so-called cop and rubber game. You can think as a cop who also does this test, and the rubber who tries to escape, and also have some ways which are the edges. And this is also some applications. And at CCT in 2016, there was some talk, or I think it's referred in our paper, about this game and how to using our strategy there. So let us start with a simple assumption. So I will start with a circle. So that's a cycle on n vertices. And later we will see that in the past it's a little bit different. And we consider again this, we write n of Cn and S like I defined it before. It's the minimal number of tests we need for a cycle and the minimal number of tests we need for a path. And of course, we can also denote instead of searching for the minimal number of questions given the number of elements, we can also search for the maximum number of elements when we are given the number of tests or questions. And again, here's the precision. So it's somehow it's the same. You can go from one to the other. So let's go for a cycle. So again, we have this example here with 16 positions, and we have an element which is moving. So it can move one step to the right, again one step to the right, and then it can move backwards, or it can also stay. So have someone a proposal of you what we can do now in this model?
Every second vertex, maybe?
Every second. But if you get then a yes, then it can move once. Then you don't know nothing, because also if you get a no, you also have to assume that that after the question or after the element still can move by one. So that means I ask a test and then it can move. But the idea to prove half of the elements is of course correct. But we do it in here's the question and so on, and what is a good search strategy. And of course, the idea is in principle okay. So we just test half of the elements, but it should be in a connected way, in this way. So let us assume this is a test here, like this. And of course, now let's assume we get a yes. And now the element is of course allowed to move one step. That means if it's here, it's okay, then it can move here. But if it's here, it can also move here. And if it's here, it can also move here. So the number of possible positions have to be extended. So if it's not a yes, then we know afterwards the element is somewhere located in this area. Yes, and we know definitely that it's not here. Okay, so the next question is of course in the same way. So the next question is now we take now the number of possible positions here, half them, it's possible because these are now 10, and ask this question here. Let's assume we get again a yes. Then of course, if the element is here, it can move here, and if the element is here, it can move here. So in the next step, these are the number of possible positions. And of course, so the next question, we ask for this 4 elements here, or we ask for this 3 elements here. And of course, because we are looking at the worst case, we always get a positive vote for the 4 elements. So in this case, if you ask for these 4 elements, we get a yes for this. And if we ask for these 3 elements, here we will get a no. We can assume in the worst case, we get a no and the element is located here. Is it clear how it works? I think it's not so difficult. But perhaps I doesn't describe it in a nice way. You can ask questions.
It is clear.
It's clear. Okay. So now, if you look now at this this thing, so we start with 16 and we reduce it to 8 and we get 2 extra positions. Then we reduce it to 10. Then we have 10. This can be reduced to 5 and we have 2 extra positions. Then we have 7 and we reduce it to 4 and again 2 extra positions. Then we have 6, we reduce to 3 and again 2 extra positions. And now we have 5 and again now we have to stop because we cannot reduce it anymore. And you will see we proved already that this strategy is optimal for S is equal 5. So that means the symbol for the circle, it's not so difficult. So in principle, what we have now a strategy and we know the best precision what we can reach is 5 because it's not possible to do better. That's also something. So if we have here to get more formal, so again we have the cycle, these are the position, these are the edges somehow, and first we prove for n is greater or equal to 5. That does not exist a successful strategy such that S is smaller or equal to 4. So it's not possible to reduce it to 4 or less elements for a cycle. That means our S star is greater or equal to 5, and the strategy which I gave you shows even that S star is equal to 5. And now the strategy, if you look at the simple strategy I gave you, it's exactly that you have 2 to the n times S minus 4. So in the case which I presented you S plus 5. So here we have just 2 to the n plus 4. So it's in principle it's logarithmic, and this plus 4 is because it can always move by 1. I think you can do it very easily and will get immediately this formula by induction if you use the strategy which I described. And of course, we could also show that the converse holds. So we can now also show that there is no better strategy. So that this one is the best possible strategy. And this can be also done simply by introduction. So we know from our strategy, we know that that it's possible to do this 2 to the n times S minus 4 plus 4. And so we have to show that it's also smaller. And the idea is that we assume that it's bigger, that it's possible to ask for more elements. And then because of this special feature that in the worst case, we always can select the bigger test part, and it can always move by 2, we can show that this is not possible. And therefore, it is proven that n equal 2 to the n times S minus 4 plus 4 is the best strategy. So that's the idea in principle, how to prove also the converse. So it's not a big deal for cycles. So next, let's look at passes. So again, we open now the cycle and roll it up, and we have here we have a path, and that means we have here boundary and we have here boundary. That means if the element can move from, perhaps I have it here, the element can move to the left, or it can move to the right and stay. But if it's here, it cannot move to the left because there's nothing. It just can move to the right. So again, some movement. And now what happened for parts? So we can, of course, do now the same thing we did for cycles. We can do this halving strategy. And then we get again, because then the element is staying in the middle. That's the counter strategy. And we get a very similar result like for cycles. But we have the boundary here. And the question is, can we use the boundaries? And it says really possible to do a better reduction. And to reduce it to 4 elements even. So our S star for parse is equal to 4. And the idea is use the boundaries. How we can do this? So our first question, again, is just we ask for half of the elements. That's this here, that's our first question. So let's assume again we get a yes. You can see it happens the same. If you get a no, then you get this part. But of course, it can move by 1. So this green thing is the possible position after the first question. And now we start doing different things now. What we do is the next question is we ask just for 2 elements here. So what happens if we get a yes? If we get a yes, of course, then we have reduced it to 4 elements, and we can give this region here. Then we give this region with 4 elements, and we know in the next step the element will be in this 4 elements here. We can bump it and okay. So if we get a no, what happens then? What happens if we get a no? Then of course it's reduced. The set of possible positions is reduced, because if you get a no here, then we know it's in this region here, and it can move by 1, so it goes here. So instead of having this, we reduce it by 1. And I think it's clear what happened now. What it is now, we ask the next question. Again, 2 here. And of course, if you get a no, then we can reduce it. If we get a yes, we are ready. So we continue in this way. Always ask 2 and reduce it and reduce it. And after some steps, so I make it a little bit faster now, we are in this situation. We have reduced it to 5 possible elements. And now if you ask to ask this for these 2 elements here, we have 2 possibilities. One thing is we get a yes. We know again it's in this 4 position, so we can give this as answer. And the other possibility is, of course, we get a no. But if we get a no, then we know it's these are the remaining step, and if the element moves by 1, then we get this 4 position. So we can, because of the boundaries of the parts, we can do better as for the cycle. So we can reduce it to 4 elements. And that's somehow the result what we also get. So that's the idea how to prove it. So if we have more than 5 positions, then there is no successful strategy such as S is smaller equal 4, but which our strategy I showed you that S star is greater equal 4. And later we proved already in the theorem that it's equal 4. So our S star for the path is equal 4. And you can think about the strategy which I presented to you. It's just n½ minus 2, because first it's linear, because if you remember, first I asked for half of the elements, and then I reduce this half by every step by 1. And so we need n/2 minus 2 steps. So, and what we get is that we have in totally the maximal number, if we put in here s equal 4, is equal 2 to the n plus 4. So it's linear in the number of questions. So the number of elements is linear in the number of questions if we have s equal 4. So, but if you know it's 5, then we can do better. If you just want to have s equal 5, then we can use a similar idea like for the cycle. And the nice thing is we can write it down in a general formula. You see, if that's the general result we have here. So our general result gives here this formula. So it gives s minus 4 times 2 to the n plus 2n plus 4. So if I put in here 4, you get the previous result here, 2n plus 4. But I can get much more if I set in here a bigger s. If I put in here 5, then I can reduce it logarithmically, and it grows exponentially somehow. Yes? Is it clear, the idea? Okay. Hopefully. So now the question is, for this simple strategy for a graph, it is possible for a path. Sorry, is it possible to give a non-adaptive strategy? And the advantage, of course, what is the advantage of a non-adaptive strategy? We don't have to wait for the previous answer. We can directly ask the next question. What is the disadvantage? So as you remember, in our adaptive strategy, we stop when we know the element is located, for example, for the parse and s equal 4. If we get a yes, when we ask for 2 elements, we can stop because we can give 4 positions where the element is located. But in the worst case, we need n questions. But if we do a non-adaptive strategy, we always have to ask n questions. And if we already found it in principle, we must track it to the end of the strategy. So we must have a strategy, even if it's find already positions, 4 positions in this example of the parse, it have to continue. And how much more tests do we need? Have someone an idea what can we do? So it was somehow a little bit surprised because Alex then came with a solution, and he said we need the same number of tests for and s equal 4. And how can we do this? His idea is, again, we took our example for n is equal 16 with a parse. So you see this matrix here. Now it's a little bit different. So this line here is are the possible positions here. So these are the n position 1, position 2, until position 16 here. And this is somehow the first question. This is the second question. This is the third question, and so on. And there's a 1 if we include the element in the question. So if we ask for element 9, 10 to 16, then that's the first question. Then we write the 1 here. And if we ask for the element 8 and 9, we put here 2 ones. Now I don't know if you see that this is in principle a very similar idea to the adaptive case now. It was a very nice idea of Alex. So because if you see here, our first question is the same we asked before. So we asked for half of the elements, that's this part. And of course, the answer could be a vote for this side, or it could be a vote for this side. Now let's assume, like in our example, that that we get a positive vote for this side. Then you see here, that's like our shifts here. Then you have this shift here. Ignore first this part here. Then you have this shift here, you have this shift here, you have this shift here, this shift here, and you stop finally here. So that means it's in principle the same idea like before, that you have here our questions for 2 elements. But of course, it could be also happen that we get a positive vote for this part of the elements. But what the fine idea or nice idea of Alex was, of course, we can ask the complement question also in parallel. The same question would be difficult because then you get 1, 1 here, and then you don't know where the element is and you cannot stop. But what you can do, you see, normally you have to ask for if the element is on the other side, you have to ask for 1, 1 in this case here. What we did for this question, we asked the complement question for this part here. We can ask for all of these elements. Of course, then we get also an answer here. And here you see we do the same. We do the normal question, but always if we have difficulties, every second question we do the complement question. So instead of asking for 1, 1 here, we ask for all ones here and zeros here. So in principle, that's exactly the same idea as for the adaptive case, that we have this first question and then we go down here and we go down here. So it's written down here. You will notice similarities, and roughly speaking, the questions are asked in parallel. And of course, you have to be sure, that's the reason why we have to change here between the questions also, that we track the element. For example, if you get a positive vote here, you must be sure that your element cannot escape, that you always know where your element is, because the final answer for the positions, that's the difference in the non-adaptive case, must be given after the final question. So you have to take sure if you get a yes already here, then you cannot stop and say, okay, I have these 4 positions here. Now you have to keeping track of the element, of course. You have to see where you get ones, and of course, at the end, you have to give this position. And this is really ensured by this strategy. You see at the end, you have here 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and so you can get the correct position with a non-adaptive strategy. And the very surprising thing, because if someone have asked me the question before, is really that we have the same number of questions in the worst case as for the adaptive. Okay, so that means our theorem, what we get, is really we have a minimum n again, so that in this case we have that the number of strategies can be written again in this form. So also we get the other form if we make it dependent from the number of questions. That was a really nice idea. Now what we do next is we ask what happens if the search element can take not just one step, but up to k steps after each test. So that means now the element is allowed to move k steps after each question. So that means it can again stay at the same point, it can move again one step, but it can move k steps. And can we generalize this this ideas we had for the simple objects here? And how does the situation change? What are the results? And the nice thing is it can be really generalized. So what we get, so our new result.
So
yes?
it is like taking the power of the graph, the case power of the graph, no?
No, not really, because now we just have the same graph, but instead he can move to the case neighbor. So he can move to the next neighbor.
I mean, you connect in the graph, you connect every pair of vertices with distance at most k.
Yes, okay, you're right. You can do it also in this way. Yes, you're right. Yes, thank you. Yes, and we find out that it's really possible. We can generalize it, and the idea is in principle always the same. And what we get there is for example, for the circle, we get this formula here. So, and you see, you find here the formula for k is equal 1, very simple. And even if we just put in here a bigger k, so it's really a nice formula what you get. And the idea is somehow really the same. We again do for the circle, it's just to analyze it. I think if someone gives it to you with a solution at the homework, the homework, you will immediately find the strategy if you know the other strategy, because it's just to do the same halving strategy, but now you get additional k positions instead of one position. And you can also do the for s is 5 again, so it's really the same idea like before. So for circles, it's very easy. So for passes, it becomes a little bit more complicated, because there's a whole region where it's different. So if n is greater equal 4k, like here, then we can do the same thing like for the circle. Then we can do the halving strategy, and instead of 1, it can move k times, and that's again easy. What's a little bit more difficult is the case when it's smaller. So because you see here for k equal 1, we get here 4, and for bigger k, you also have some results here. We also show that this S star is equal to this, but in between, so you have a whole range from 3k plus 1 to 4k, and there it's different because of the boundaries. Now, if you look at this the same idea where we first asked for 2, we have now asked for k plus 1, and now it depends a little bit of the boundary. That's the reason why for several S star you have to look at many cases. That means in this case, you see you get some more results from 2k plus 1 to 3 to 4k plus 1. So yes, you see here these cases we denoted here by YL. You have this. You have the decided between if L is between 1 and k, and if now our S is between 3k and 4k, so we have here plus L somehow, then we are in the case where we can make this trick again by asking for this intervals, and depending on this L here, we get here 2nl plus 4k. And in the other cases, so if S is greater equal 4k, it's like for the cycle. Then we get this formula. But we cannot write it in a nice form in one formula like before. We have in principle two equations here. So the other thing what we are doing is we were looking at trees. So that's the old paper. So this non-adaptive case, that was a paper with Alex, and the fast element, that was a paper with Alex, and now we are back to the paper with Nando, Haru, and Valotte. So there we also looked at trees and looked how we can find the elements in trees. So first we look at, I think it's easier to look at binary trees, how much we can reduce the elements there. And the idea there is really we looked at complete binary trees, and then we have to always branches. And the idea is also always that you want to avoid that it comes out and goes over the root out and go in a separate branch. So somehow you always have to trust that your element do not escape over the branch. And if it escape over the branch, then you always have so many elements that you can locate it there and stop there. That's the main idea of the branch, but the analysis is somehow complicated. You have to go over a lot of cases. I think we did it nicely for binary trees with a lot of pictures in the paper. If you are interested in this, I think you can try it by yourself also. It's somehow really the same, similar idea like for the cycle or like for the parse, you always have to look at some sets and look where can it escape and for what kind of sets can I ask and where can I stop and which are best possible sets. And you have a lot of cases there that makes it different. So, and the result get a little bit better and a little bit easier if we allow the command only to move t times. So what you can do is also to say, instead of what we looked at the moment, we looked always at the case where the element is allowed to stay or move every time. After every question, it can move. But like you know, a lot of results for searching with lies, also for searching with movements, you can also restrict the number of movements. And what we do is we restrict it to t movements. So that's also an idea that we say, okay, instead of allowing every time a movement, we allow that it can only move t times. And in this case, we looked it up for the cycle and for the parse again. And of course, you get some advantage because if you see it can only move 2 times. And then we got this two formulas here. That's another result we get here. And only an exact formula we get for the case of t equal 1 and 2 and s equals c, because of course if the number of movements are restricted, then you can have a better precision as if it's not restricted. Then you can put them, for example, to the boundary, and if you know it moves several times already, then you can give better precision. Yes, what did we do? So somehow it's still a lot of things are open in this. I just want to give you some ideas of what we did in this and how it works and what one have to do to analyze it. So we also, I think we didn't publish, we also looked at some other graphs and try to solve it. But there we got our lower and upper bounds are very far away, and so we didn't include it in the paper. But perhaps there are some interesting graphs which are also for practical things relevant at which you can look. And what we want to do is first to look at simple graph like cycle and parse, and more complicated is the tree perhaps, and see what we can do. But if you got the idea for cycles and parse, then you know what to do for complicated graphs. But unfortunately, the strategy, somehow it's clear what one should do to get somehow a good strategy, and also a little bit more difficult is perhaps the converse. But in principle, I hope you get an idea what one have to do if you want to analyze a more complicated graph. And what I want to motivate you, perhaps look for other graphs which are interesting, try to find strategies, and still in there are open questions for trees. So you see there are only bounds just, and also for other interesting parsers and for special graphs, it's not clear what happens there. And what were some things where we looked at it, and we really get big gaps at the moment, and there's, for that reason, so even at the time when we did the work with Nando, Volodya, and Harut, we start to look at n cubes, but somehow it was not satisfying what we got. But of course, perhaps someone is interested of you and also looked at this problem and get some better ideas or some new ideas to look at this. And of course, one can think, of course, perhaps first in the simple model, one can also do what always is done if some tests are incorrect, that we didn't look at this at the moment. And of course, one can also look at related coding problems. For example, for coding, if you want to send, if you have a cycle and want to send the position to a receiver, then you can use, of course, our adaptive strategy for a channel with feedback. Then both knows the questions, like, I think you should know this from my last talk. Then you can do this idea that you have this equivalent formula, this equivalent formulation for coding and searching, and then you can use it. You have a cycle, and you have an element which is moving, and you want to transmit somehow, yes, the position of an element with a certain precision, and you always answer the question and transfer it to the receiver. That's also some relation to coding. Yes, so then I would thank you for your attention.